We can compare how easily a substance can be reduced or oxidized by looking at the standard electrode potentials. So I'm giving you here just two examples, and then I will show you where I'm taking these numbers from. I have two half reactions, and you know that it's a half reaction because it's showing the electrons. Okay? So you have zinc plus 2, the ion of zinc plus 2 electrons going to zinc solid, no charge. And we have a number, negative 0.76, that's the electrode potential for the reduction of zinc. And then I have another one for silver. The ion of silver with a charge of plus 1 electron going to silver solid, no charge. The potential for that half reaction is 0.80. The unit is volts. So we can look at those two numbers, and based on the numbers, we can think about which substance is going to be oxidized, which substance is going to be reduced. The electrons will always move from where you have your oxidation towards where you're reducing something. That's what I'm showing you in the diagram. So you're getting the electrons, or the formation of the electrons. It's happening where you have the substance with the more negative potential. So if you check your two numbers for your reduction reactions, here you have negative 0.76 volts for zinc, 0.80 for silver, which means that out of those two, the one with the more negative potential is the zinc. That's the one that is going to be giving electrons away. Now, the electrode with the less negative potential will be the one, or the half reaction that you have for the silver. So you have oxidation and reduction. But in your half reactions, you have ions and you have the solids. Which substances are being oxidized, which substances are being reduced? By looking at your reactions here, you know that the more negative potential will go first in my diagram, where I have electrode 1. So the substance that is being oxidized, it has to be in that half reaction that you have for the zinc, based on your potential. Now zinc plus 2, it already has a charge. Zinc plus 2 already lost 2 electrons. Okay? So zinc plus 2 is not the substance that is being oxidized. If zinc plus 2 is oxidized, losing 2 electrons, it will give you zinc plus 4. Okay? You already have a positive charge of 2, and you're losing another two negative charges that will go to zinc plus 4. The substance that gets oxidized is zinc the solid. So when zinc solid is losing electrons, it will form zinc plus 2 electrons, which is the same reaction that you have but flipped. Your reaction represents a reduction, something gaining electrons to give you a product. So the oxidation half reactions is the same as your reduction reactions but flipped in the opposite direction. Your zinc solid, it's being oxidized to zinc plus 2 electrons. Those electrons are the ones that are moving from where you have your electrode with more negative potential, electrode 1 in this case, towards electrode 2, where the reduction is happening. So on the right side of your diagram, we have the silver. Now the reaction that you have for the silver is already a reduction reaction, where you have silver plus 1 gaining 1 electron, to give you silver solid. So the electrons that you're forming from the zinc, when zinc is being oxidized, you're getting your electrons. They're moving towards where you have your ion of silver. The ion of silver is gaining the electron to become reduced, giving you the ion, the silver solid that you have on the product side. There's another way of determining how this reaction between the zinc and the silver is going to happen. We can use this equation here to calculate the cell potential for a galvanic or voltaic cell. The overall cell potential is just a difference between your electrode potentials. If you calculate your number and you get a positive value, it means that you have a spontaneous. Spontaneous reaction is what we have in galvanic or voltaic cells. So for you to get a positive number here using this equation, you need to have the more negative potential in the anode, which is what we did. The more negative potential corresponds to the half reaction that you have for the zinc, which is negative 0.76. Now the less negative potential, which in this case it's a positive number, but you can have both negative, both positive. In this case you have a positive number for the less negative. That one is your 0.8. Units of volts for both. So you can calculate your E cell 0.80 minus negative 0.76, which is going to give you a positive number equal to 1.56 volts. So between the zinc and the silver, the zinc solid has to be the one that is oxidized. If you have the silver solid as being oxidized, your potentials will be flipped and you will get a negative number, which means that you're arranging your numbers in a way that is going to give you a not spontaneous reaction. So whenever you get a cell potential that has a positive number, that represents a spontaneous reaction. In this case, the silver will take the electron, silver plus 1, the ion of silver will take the electrons from the zinc solid. So zinc solid is the one that is losing the electrons, and the electrons are being transferred to the ion of silver. So the numbers that I show you for the half reaction of zinc and silver, they're coming from tables where we have the standard electrode potentials. Standard electrode potentials because those values are determined at room temperature, atmospheric pressure, and using solutions with a concentration equal to 1 molar. So I'm giving you just some examples here in this table. So I have on the very top of the table, I have gold, and what I'm showing you is the half reactions that represents reductions. So you have there starting with gold, the ion of gold gaining 3 electrons to give you the solid, and for that one you have a potential that is positive 1.5. All the way to the bottom of the table you have the ion of magnesium gaining 2 electrons to give you magnesium solid, and for that one you have a potential equal to negative 2.37. All of those numbers are in units of volts. So you have a trend with your numbers. You're going from the largest positive number to the largest negative number, or the smallest one, all the way to the bottom. The higher they are in the table, the stronger oxidizing agents, which means that, remember, the oxidizing agent is the substance that is being reduced. Oxidizing agent is responsible for the oxidation of something else. So if your substance is responsible for oxidizing something else, it's because that substance is getting the electrons. Okay? So some things that are easily reduced are on the top of the table. Things that are easily oxidized, giving away electrons, are all the way to the bottom. Now, you can use the signs also to guide you. Things that are very negative, it means that negative electrons are negatively charged. So you can think about this potential as a very negative number. They want to give electrons or negative charge away. That will come easily for something that has a very negative potential, giving negative charge away. Things with a very positive potential. Remember, we start at 0. Same number of positive and negative charges, right? Your elements with no charge at all, they have no charge at all because you have the same number of protons, positive charges, and electrons. So the more positive a substance is, the more negative charge will need to go back to 0 again. The more negative something is, the more negative charge something has to give away to go back to 0. So things that are very positive, okay, with a potential that is very positive, they actually want to get a negative charge. Things with a very negative potential, they want to give negative charge away. So if you need potentials for any possible calculations, you can use this table. If you're given them, then you can use the potentials that you have been given. So with this example here, which is the same potentials that we used previously, we're going to do some things. We're going to combine these two half reactions to get an overall reaction, balancing by mass and by charge. And also we're going to use these two half reactions to write down a representation for a redox reaction that is known as cell notation. So we already did this calculation here to get the potential for the cell when you combine your two half reactions. So we have that number that was 1.56 volts as a positive number because this represents a spontaneous. Now you have your two half reactions, one representing the oxidation. That's what you have in the anode. Anode is oxidation. So the oxidation is happening in the anode. So for your oxidation reaction, you need to flip the reaction that you're given as a reduction. You don't have to change any signs for the potential at all. This is just actually representing the oxidation. The zinc solid is the one that is being oxidized, not the ion of zinc. So zinc solid giving you zinc plus 2 electrons, that represents the half reaction of what's happening in the anode where the oxidation is happening. Now we have the half reaction for the reduction of silver. So you have your ion of silver plus 1 electron going to silver solid, no charge. From those two, we can get the overall reaction that it's actually happening. So I'm going to copy my reactions here. Now, you don't have to put them in the same order that I have them here. It will give you the same final reaction. I'm writing down my reduction first, and I'm writing down my oxidation under. when you have an overall reaction, the overall reaction will never show electrons. The overall reaction is an overall reaction because the electrons that are being formed and used up, they're being canceled out. If you look at your two half reactions, for the reduction of silver plus 1, you need 1 electron. From the oxidation of zinc solid, you're getting 2 electrons. Your number of electrons is not the same, which means that you need to actually balance by charge. You need to have the same number of electrons on both half reactions in order for your electrons to be canceled out. If you want to have the same number of electrons here, you have to multiply the whole reaction by a factor. If you need 2 electrons, because that's what you're getting from your oxidation, I'm going to multiply everything here by a factor of 2. And now I'm going to write down my new equation down here. That will give you 2 ions of silver plus 1, plus this is 2 times 1 electron, that will give you 2 electrons, going to 2 Ag solid. Now you have the same number of electrons in your half reaction for zinc as the number of electrons that you have for the reduction of silver. 2 moles of silver plus 1 will gain 2 electrons that are coming from the oxidation of zinc to form 2 moles of silver solid. So you're getting your 2 electrons from the oxidation of zinc, and those 2 electrons are being used up in the reduction of your silver ion. So your electrons are canceling out. They will cancel out because you have the same amount. If you don't have the same number of electrons in each half reaction, then you cannot cancel the electrons out. So now we can add the reactions because your electrons are canceled out. That will give you zinc solid here plus 2 silver plus 1 going to zinc plus 2 plus 2 silver solid. Zinc solid, it's been oxidized to zinc plus 2, and your silver here, it's being reduced to silver solid. Oxidation number, it's increasing. For zinc solid, that's your element, oxidation number it's 0, and you're going from 0 to oxidation number equal to plus 2. Oxidation number it's increasing, that one is being oxidized. For silver, the ion of silver with a charge of plus 1 gaining electrons to give you the element silver as a solid with an oxidation number equals to 0. Oxidation number it's being reduced, so that's the reduction right there. So you can be given the half reactions for you to calculate the cell potential, or you can be given the overall reaction and you have to use that one to calculate the cell potential. So in this example, you have an overall reaction. You have your 2 moles of aluminum solid plus 3 moles of iron plus 2, giving you 2 moles of aluminum ions with a charge of plus 3, plus 3 moles of iron solid. So the solid here, aluminum, has an oxidation number equals to 0, and that's going to aluminum plus 3. So that's being oxidized. And oxidation happens in the anode. And now we have iron with a charge of plus 2 going to a charge of 0. That represents the reduction, which is what's happening in the cathode. So if you need to calculate your cell potential, you're given the potentials for both half reactions. What is happening in the cathode, this is E cat. What is happening in the cathode is the reduction of your iron ion, and for that one we have negative 0.45 volts. What is happening in the anode is the oxidation of aluminum, and the potential for that one is negative 1.66 volts. So when you do your negative 0.45 minus negative 1.66 volts, that will give you a positive number, and that will be 1.21 volts. So you can be given two half reactions for you to calculate the potential of a spontaneous cell. So you have to arrange your potentials to get a positive number. Or you can be given an overall reaction, and then from your overall reaction you have to be able to identify which substance is being oxidized, which substance is being reduced, so you can plug in your numbers properly in your equation to calculate the potential. Now, the cell notation is something that we use to represent oxidation and reduction also. It's a simplified version, but it will give you all the information that you need to know which substance is being oxidized, what you're getting from the oxidation, which substance is being reduced, and what you're getting for your reduction. So cell notation has always the same it's the same way that we use all the time to write down your cell notation. We start with the substance that is being oxidized. So looking at your reaction, what is being oxidized is aluminum solid. Your aluminum solid is being oxidized to aluminum plus 3. So I start in my cell notation with what is being oxidized, and that's the aluminum solid. Now we follow that aluminum solid with a single line. Your aluminum solid is being oxidized to give you aluminum plus 3. So aluminum solid is being oxidized to aluminum plus 3. After that, we write down a double line. The double line represents where your half reaction is over. So my first half reaction that you're showing here is showing you what is being oxidized and the product of that oxidation. You're done with that half. Now the following half will show you the reduction. What you're getting from your reduction. You have the ion of iron is the one that is being reduced. You have iron plus 2 going to iron 0. So I have here iron plus 2, single line, so the cell notation is showing you, okay, aluminum solid is being oxidized to form aluminum plus 3, and that's what I have in my anode. Where the oxidation is happening. Always oxidation first in your cell notation. And then you have what's happening in the reduction part. For your reduction, your ion of iron, it's been reduced to give you iron solid. And that's what you have in the cathode. With the reduction it's happening. So always first half, what you have in front of that double line, it's the half reaction that you have in your oxidation part, which is the anode. And then what you have on the right side of that double line is representing what's happening in the cathode, where the reduction is happening. So something else that you have to be able to do, look, you can be given your half reactions to find out your potential. You can be given the whole reaction to find out your potential. And something else that you can be asked is to find out if a reaction is spontaneous or not spontaneous based on the actual reaction that it's given. Looking at the reaction here, iron plus 2 is going to iron 0. That represents a reduction. Which is what goes in the cathode. Copper 0 going to copper plus 2. That represents the oxidation, which is what goes in the anode. So to find out your cell potential, we write down the equation. That's whatever you have in the cathode as being reduced minus what you have in the anode as being oxidized. So for the cathode, what is being reduced is your iron plus 2 from plus 2 to 0. So that's a negative 0.45. Then what is being oxidized is the copper from 0 to plus 2. So that will be minus 0.34 volts. Just by looking at what you have here, you will get a negative number. That's a negative number minus a positive number. Subtraction is the same as addition of the opposite. So this is the same as negative 0.45 plus negative 0.34. So you're technically adding two negative numbers, which is going to give you a negative potential. So if you add these numbers in your calculator, negative 0.45 minus 0.34, that will give you negative 0.79. A negative cell potential right here that represents a not spontaneous reaction. So how your reaction is written right there, your copper is not going to be strong enough to, like your ion of iron is not going to be strong enough to take electrons from your copper solid. That's not going to happen, and you know that based on that negative potential. If you get a positive potential, then it means that the electrons can be removed from one substance, the one that wants those electrons, from the other substance. But the negative potential is telling you that your iron plus 2 is not going to be strong enough to pull the electrons from your copper solid. Now we're going to relate the cell potential with things that we learned previously. So you have your cell potential given by the difference between your two half reaction potentials. Free energy, that's your delta G, your Gibbs free energy. And then the equilibrium constant is K. So first I'm going over the relationship between your cell potential and that standard cell potential, because you have concentrations equal to 1 molar, room temperature, and atmospheric pressure. And that will be also your delta G's are standard values. So I have this equation here. So these calculations are pretty simple because you're just plugging in numbers in the equation. The value of N is just how many electrons are being transferred. How many electrons you're getting from your oxidation, how many electrons are being used in the reduction. F, it's a constant, so you have the value right there, 96,485 coulombs. So that's the unit of charge. And then the E cell is just the cell potential that we calculate doing this, the potential for your half reaction, the reduction, what you have in the cathode, minus what you have in the anode. So I have one problem here, and we have a conversion factor right here. The numerical values in your conversion factor is equal to 1. So the numerical value in your problem is not going to change. But if we're calculating delta G, that's an amount of energy, right? It's Gibbs free energy. An amount of energy is calculated in joules or kilojoules in units of energy. That's why we need that conversion factor right there. So first, let's look at the problem here. You have manganese solid going to manganese plus 2, and you have nickel plus 2 going to nickel solid. You have your two half reactions right there, and you have the potentials for each one. You need that to calculate the cell potential. In your equation, you need the number of electrons that is being transferred, the constant, and the cell potential. So I'm going to write down here my cell potential, which one is being reduced because it's cathode first, so nickel plus 2 to nickel solid. That represents the reduction. So that will be negative 0.23 volts minus. Oxidation goes right here, manganese solid to manganese plus 2. And for the reaction for manganese, we have negative 1.18 volts. And you can get your E cell. So negative 0.23 minus negative 0.118, 0.95. So out of the three things that we need in the equation, because we're trying to calculate the Gibbs free energy, I already have my cell potential. That's the only one that you have to actually calculate. The value of F you have, but look, the value of F is given in units of coulombs, okay? Units C for charge. The cell potential that you're calculating, it has units of volts. That is why we need that conversion factor right here. If you have 0.95 volts and 1 volt is the same as 1 joules per coulomb, you can replace that unit of volt for joules per coulomb, and you will see why you have to do that. Now, another thing that you need to plug in your equation to calculate that delta G is the number of electrons that are being transferred. If you look at your two half reactions here, the oxidation is happening in your manganese. Manganese solid is going to manganese plus 2. So you have 2 electrons from the oxidation of manganese. And the one that is being reduced, it's nickel plus 2 to nickel solid. And you have 2 electrons for the reduction. So every time manganese solid is being oxidized to manganese plus 2, you're getting 2 electrons, right? Your manganese plus 2, you have a charge of plus 2 because it's manganese solid is losing 2 electrons to give you that manganese plus 2. Every time 1 mole of nickel plus 2 is being reduced, it's gaining 2 electrons. It's not a total of 4 electrons. The electrons that are being transferred is 2. You're getting 2 electrons from the oxidation of manganese, and you're using up 2 electrons in the reduction of nickel. So the value of N for this example here is 2 electrons. So now you have everything that you need to calculate your delta G. That's a 2 for your 2 electrons. 485 coulombs. And then your cell potential is 0.95 joules per coulomb. If you don't have joules per coulomb here, that unit will be volts, and you have nothing to cancel out that unit with. Right now, you have your coulombs here and here, which means that whatever number you're calculating right there will have unit of joules, which is units of energy. So you have 2 times, this will be a big number because you have 96,485 times 2 times 0.95, 1.83, ten to the 5 joules. So you have 1.83 times 10 to the 5th joules. That's the value for the delta G for this reaction that you have between manganese and nickel plus 2. You can be asked the same type of calculation, but finding the value of the delta G in kilojoules. So if you need kilojoules, you have to convert your joules to kilojoules to get the final answer. The second type of relationship that we're going to be looking at is the cell potential with the equilibrium constant. And for this one, this is also another calculation with a different equation. So you have one equation to find out the delta G, and now you have an equation that we can use to find out the value of that equilibrium constant. So we have a problem here, and with your problem, you're trying to find out the equilibrium constant. That's what you want to calculate. Which is K. So in my equation, the numerical value of N, again, it's how many electrons are being transferred. Now, in the previous example, you were given the half reactions. So from your half reactions, we were looking at how many electrons you had for the oxidation, how many electrons you were using for the reduction, and that was it. In this one, you're given the overall reaction, and you have to determine how many electrons are being transferred from that overall reaction. It's not difficult. Okay? So I'm going to check which one is being oxidized. It's being oxidized, the iron solid to iron plus 3. So that's your oxidation here to here. The reduction is happening with the hydrogen ion plus 1 to 0 here to here. Remember, the same number of electrons that you're getting from the oxidation, it has to be the same number of electrons that you're using for the reduction. So your iron solid is going from an oxidation number equal to 0 to plus 3. So that's the change in your oxidation number from 0 to plus 3, which means that your iron is losing 3 electrons, but you don't have 1 mole of iron, you have 2 moles of iron. Each mole of iron is losing 3 electrons, which means that if you have 2 moles of iron, the total number of electrons that you're getting from the oxidation of iron is 6 electrons. Each one is losing 3. So 1 mole of iron is going from 0 to 3, and then another mole of iron is going from 0 to 3. So you're getting 3 electrons for each mole, which is a total of 6 electrons from the oxidation. So I'm looking at how many electrons I'm getting from the oxidation. Now you can do the same thing with the reduction. It doesn't matter which one you use, you should get the same number, because the number of electrons that you're getting from the oxidation it has to be equal to the number of electrons that are being used to reduce the other substance. So you have 6 protons, each one with a charge of +1. So H plus, 6 of them, right? And you're forming on the other side hydrogen. So two protons, each one is gaining 1 electron to give you H2. So if you have 6 protons and you're getting 0 on the other side, that's your oxidation number for hydrogen, that's 0. It means that each proton is gaining 1 electron. Since you have 6 protons, right, and all of your protons are gaining electrons, all 6 of them are gaining 1 electron each one, you have 6 electrons. For the reduction of your proton H plus from +1 to 0. So in total, the number of electrons that is being transferred is 6 electrons. You're getting 6 electrons from the oxidation and you're using up 6 electrons for the reduction. So the value of N is 6 for this example. So in your problem, you have the value of E cell, it's given 0.036. So that number 0.0592 is part of the formula, okay? It's always the same number for your equation. 6 electrons, and that will be times the log of K. So I'm just rearranging my equation to solve for K, okay? So I need to isolate this part here so then we can get rid of the log. So to isolate that part, I need to remove all of this. So that will be times 6 over 0.0592. That will cancel out here, here, and you have only the log of K. But you have to do the same thing on both sides. So this will be 6 So I'm canceling out all of that term on the right side of the equation when I have where I have the log of K. So you have to do the same thing on the left side of your equation. So you can use your calculator now to get how much is 6 times 0.036 divided by 0.0592. And now to get rid of the log, the inverse function of the log is 10 to the, so 10 to the, all of this right here, okay. That will cancel out that, and you're getting just K. 10 to the raised to the power of all of this in that parenthesis will give you how much is K. A big number. I have 4.45 to the third. Okay, so in the thousands. You can get something close to that number depending on if you calculated this number here, how much this number is. And then you plug in that number in your equation for 10 to the whatever number you're getting, you will get something a little bit different from this one here, but that's okay. So you have a value of K in the thousands. The value of K, right, is telling you how much product you have when the reaction reaches equilibrium. You have a large value of K, which means that you can assume that this reaction goes to completion. When the reaction reaches equilibrium, you have mostly everything that you have present. It's a product because you're calculating K, that's concentration of product over concentration of your reactant. The larger the value of K means that you have more of your product and just a small amount of reactant left, or you can assume that there's no reactants left because you got a big number. Usually, if you have a numerical value for the cell potential that is a positive number, it means that that reaction is spontaneous. A reaction that is spontaneous means that it will happen with no outside intervention. It wants to actually, your iron solid wants to give electrons away spontaneously. So if that's a spontaneous reaction, you should expect to get a large numerical value for your equilibrium constant because your reaction wants to go to your product side. So you can expect that if you have a numerical value for the cell potential, which represents a spontaneous reaction because you have a positive number, you can expect to get a large numerical value for the equilibrium constant. Now the last one, and this example that I'm using here is something that you already saw before. All of the calculations that we have been doing is under standard conditions, which means that we're not using any concentrations because all the concentrations are equal to 1 molar. Now in this example here, we're using non-standard conditions. So the concentrations are different from 1 molar. So we don't calculate the cell potential using the equation cathode minus anode because when we're using that equation, those numbers that you have in the standard potential in the table that I showed you in the beginning, all of those numbers are calculated under standard conditions. So to calculate a cell potential when the concentrations are different from 1 molar, we use this equation here. It has a name. That's the Nernst equation. Your equation, you have the term for your standard cell potential there. So we're actually doing a correction to that value. You will get a different value because now the concentrations are not equal to 1 molar. The second term is the same that we used in the previous equation, 0.0592 volts divided by N, which is the number of moles of electrons that are being transferred in your reaction. And now we have something different here. The log of Q. Q, it's like K, okay? K is your equilibrium constant. Q represents the same thing, concentration of your products over concentration of your reactants. Same thing as your equilibrium constant. But, and remember, like your concentrations are raised to the power of whatever coefficient you have in the equation. The difference between Q and K, when you're calculating K, the concentrations that you're using are concentrations at equilibrium. When you're using Q, the concentrations that we plug in to get Q are concentrations at any moment during your reaction, any moment. You don't have to wait for the reaction to reach equilibrium so you can get the concentrations. You don't have to do that with Q. So usually when you have a problem where you have to use the Nernst equation, it's very easy to identify that you need to use that equation because you're going to be given concentrations. For all the problems that we did before, you were not given concentrations because all of them were equal to 1. Now in this one, you are given concentrations, which means that we have to use the Nernst equation to find out the potential for this one. So what you're trying to calculate here is the cell potential at non-standard conditions. That's what we're trying to calculate. So you have E cell here, non-standard. The degree symbol right there is what we use for standard conditions. So you can check in your notes because we calculated the cell potential under standard conditions for this reaction here between aluminum and iron. We did that one in the beginning. So for that reaction right there, you can check in your notes, you have a standard cell potential. I'm not going to calculate that one again, but it was 1.21 volts. Okay? So that's the cell potential that you will get if the concentration of your solutions for both the iron plus 2 and the aluminum plus 3, if your concentrations are equal to 1 molar. Now, you don't have 1 molar here. Look, you have concentration for the ion of iron plus 2 is 2 molar. Concentration for your aluminum ion is 0.01 molar. So I'm going to start by writing my equation, and that will be E cell non-standard. That's what you're calculating. 1.21 volts. That's the cell potential for your reaction under standard conditions, and we calculated that one previously. Minus number of electrons that are being transferred in this reaction. If you check your aluminum solid here, oxidation number 0 is going to +3. 0 to +3, it means that it's losing 3 electrons. But we have 2 moles of aluminum, so each one is losing 3 electrons. So you have a total number of electrons of 6 from the oxidation. The reduction is going to give you the same number. You have iron plus 2 to iron 0. So +2 to 0 is gaining 2 electrons. But you have 3 moles of iron, so each mole is gaining 2 electrons, and you have 3 moles, so that will give you 6 electrons. So you're getting 6 electrons from the oxidation, and you're using up 6 electrons in the reduction. So the total number of electrons for this reaction is 6. Log of Q. Q, it's products over reactants. So if you check your reaction, your product is 2 moles of aluminum plus 3 moles of iron solid. Now your equilibrium constant, the concentrations that you use in your equilibrium constant are concentrations for gases and aqueous substances. You don't include concentrations for any solids or liquids. which means that concentration for iron solid, you don't need that in your value of Q because Q is the same as K. All of your ions, all of the ions that you have been saying in all of the reactions, ions are always aqueous. So aluminum plus 3, that's your product right there. Concentration for aluminum plus 3 is 0.01 molar. That's concentration. And you have a coefficient that is equal to 2. So remember that your concentrations are raised to the power of whatever coefficient you have. That's for the products over the reactants. On your reactant side, you have again aluminum solid, that's a solid, is not part of Q. And then you have iron plus 2. Concentration for iron plus 2 is 2.00 molar. Raised to the power of whatever coefficient you have. For that one, it's a 3, so that's to the third. And now you can complete your calculation. This is 0.0592 divided by 6 times the log of all of this here. So you can do everything. You will get something close to 1.26. 1.21 minus 0.0592 divided by 6 times the log of 0.01 squared divided by 2. Yeah, I have 1.2583. That will give you, all of this will give you a number with units of volts, and you have volts here. So your final number, it's in units of volts. So the difference in your potential that you have for the reaction under standard conditions, that number is 1.21. Now changing your concentrations will give you a number that is 1.26. The difference between those two numbers is because of the difference in concentration. The number of electrons that it's being transferred in your reaction is the same when you have standard conditions and when you have non-standard conditions. The number of electrons is not changing, your reaction is the same. But now what is different is the given concentrations. Your 1.21 is what you get when the concentration for both ions is 1 molar. Now in this case you have something different, which means that that potential that you're calculating will be different depending on which concentrations you're given.